Copyright in these lectures is either owned by the ANU or a third party who has licensed the ANU to use it. Students may use the recording for personal study only. No lecture may be communicated online, copied or shared without the prior permission of the ANU.
All right. So first of all, I post our assignment 2 on the Walto 2 days ago, and I sent everybody a message. And this is basically this assignment count for 10 points. And you can do it individually, and you can also have a group of 2. And each group only needs to submit one copy of your result. And you submit your result online through Walto. You don't have to print it out. But you do need to you need a cover page, not paper-based, but with your Excel spreadsheet and submit it online through Walto. And the due date is you have roughly 2 weeks, a little more than 2 weeks, 15 days to complete this assignment. And this assignment, basically, I provide you 5 different assets. The stock market, I use SP 500, so this is basically a stock market. This represents commodity, I use oil fund, right? And this is so-called emerging market index. It represents some international markets, most of them equity markets, but not including the US. And this is US bond index. So this is another class. And this is currency market. I use dollar index. So you have 5 different assets, and you will make a portfolio, optimal portfolio out of those 5 assets. And the answer is you want to give solution. If you read through, I don't want to read words by words, but basically you want to find the optimal allocation. And how to find the optimal allocation? You find the highest possible Sharpe ratio. That's the only way. So your solution is, this is the solution I want to. You need to fill in all this empty cells with number, but your final answer should be this, always this one. This is very similar, solution B, solution C. I will just look at your Sharpe ratio as the final answer, right? So you will do the optimization based on the Sharpe ratio. You will find the highest possible Sharpe ratio by changing the weight of each asset, right? You have 5 assets, so you have 5 weights. There is one optimal weight which can provide you the highest possible Sharpe ratio. And if you do that in spreadsheet, you will need something like a solver to do that. So you will need to install. If you haven't installed that, you need to add in and solver. Do you see this? Solver, then go. Okay, solver, adding, okay. Now in the data step, you have the solver. You are going to, so the solver allows you, this is objective. So our objective is this cell. Your Sharpe ratio should max. Max this Sharpe ratio, this cell. Then by changing the variable cell, this is your variables. This is actually your 5 weights, right? Those 5 weights. This is something you can change. So you will choose those 5 weights as your changing variable cells, subject to a constraint. An obvious constraint is the sum of those 5 weights should equal to 1, right? That's an obvious constraint. And you have to make that this plus this all together equal to 1, then as a constraint. Then you just, this doesn't matter, you just choose the first one, nonlinear. And don't click this, make unconstrained variable non-negative. For the solution A, you don't have to have this additional constraint, right? So you don't want to click this. Then you can solve it, right? And of course, to do the solver, you have to put in some initial value, right? You cannot just let all those weight blank and let this Excel to do this job for you. So my suggestion is, first of all, maybe you can try just put equal weight 0, 0.2, 0.2, and 0.2. So you can put an equal weight. This is just initial. It's not a solution. But the solver will start from this initial weights, and they will do the calculation background and eventually figure out optimal weights, right? So this is how typically you do it. And of course, you will need this variance covariance matrix to calculate the portfolio standard deviation. And if you forgot how to calculate portfolio standard deviation by variance covariance matrix, just go back to our slides or textbook. It's just a simple mathematical formula. And once you have this standard deviation and portfolio, remember this is excess return, right? Excess return is portfolio return minus the average risk-free rate. And I already provide you risk-free rate here. So you need to calculate the average monthly risk-free rate, then you can have excess return. But remember, after you do this and that, all you get is monthly, right? This is a monthly return every month. And this standard deviation you will have is monthly standard deviation, monthly excess return. Then if you just divided this monthly excess return by monthly standard deviation, that's just monthly Sharpe ratio. But typically we want annualized Sharpe ratio. How to do annualized Sharpe ratio? It's very easy. Just square root of 12. Square root of 12. Then times what you get from monthly Sharpe ratio. Why square root of 12? Because return increases with proportional to time, but standard deviation increase proportional to the square root of 12. Square root of time. Then 12 over square root of 12, that's just square root of 12. So annualized Sharpe ratio equal to square root of 12 times the monthly Sharpe ratio. Is everyone clear about that? So, and of course, our tutors are going to mark your assignment. But the thing is how those tutors are going to mark your assignments. Because this is programming, they cannot check your every step. They cannot check whether you do the programming right or wrong, because we have hundreds of students. So we can only look at your result. That's the only standard to give you mark. So let's suppose the right answer is 1.1111 here. Please keep at least 4 decimals. So this is 1.1111. Suppose this is our right answer. If your answer is this right answer plus 0.005 minus 0.005, if your answer is in this range, then you can get full mark, 10 mark, okay? So I don't have to say how your final mark depends on your result. So if instead you're out of this range, but you belong to plus 0.005 minus 0.005, if you are not in this range, but your result is in this range instead, probably I will give you 6 mark, right? And if you're still far away, then your mark will reduce further. So that is how the tutor will mark your result. Does everybody, okay? just use portfolio standard deviation, because I think just the standard deviation of returns, not the standard deviation of excess returns. Okay.
So for risk-free return, we can just use the average.
Say that again.
So to calculate the risk-free return, we can just use the average of.
Yeah, you can just use the average of risk-free rate. You don't have to minus the risk-free rate every step. All you need to do is, you don't need to care much about the risk-free rate until the last step, until here. Then you minus the risk-free rate. Okay. Before this step, you don't need to worry about risk-free rate. And I think that's a good question. Actually, the standard deviation of excess return is a little different from standard deviation of return, because the risk-free rate is not really constant in real world. And what's the difference between A, B, C? If you figure out A, B, and C would be very easy. They're basically the same. The only difference is do A again, but some additional constraint. For example, B is do A again, but this time you are not allowed to short asset. What does that mean? That means your portfolio weights for each asset should be non-negative, right? So all those 5 weights should be positive. So you just put additional constraint that each of those cells has to be non-negative. Then do the same solver again. And for example, the solution C, you just have another constraint, like the single type of asset can't exceed 30%. So just put some extra constraint in your solver, all those constraints, 8, 8, 8, then you got it. Yeah? Okay. That's basically. So I cannot, because this is assignment, I cannot answer some question like, can you double check whether my methodology is right or wrong? I cannot reply email like that. Only I can reply emails if you find there is some kind of error in this question set. If you think the whole question doesn't make any sense, something wrong, send me email. Or you are not clear about this basic setting, you can send me email. Otherwise, I cannot reply other type of emails because for the fairness to everybody. All right? Any other questions? Okay.
Do we need to put in for solution A, B, and C? We need to put in for the measures, whether weighted variance and covariance metrics or just the variance covariance metrics.
Say that again. Sorry, I didn't hear you clear.
For the solution A, B, and C, we need to put in variance covariance metrics. So that is weighted variance covariance metrics.
It's not weighted. It's just a simple variance covariance measures. But basically, I'm not going to mark your result based on your number here. This is just convenient for you to do the calculation. So if you don't want this part, you can remove this. What I'm saying, if your whole purpose is get full score, this part is not really important. I think those tutors will not look at those numbers here. Because they have hundreds of different copy to grade, they will only look at those 3 numbers. This is the most important one. All right. So this is about our assignment. And don't forget about due date, because late submission will not be accepted. That's our rule of our class. And it happened again and again before. Some students forgot 1 or 2 hours late and come to my office, ask, can you make an exception? I said, I'm sorry. Yes. I hate to say that, but I have to say, if you are late. So we continue with this chapter, and I'm not sure we can finish this or not. We'll try. So we are talking about interest rate risk. Interest rate risk is one of the main risks if you have a bond portfolio. And how to measure this interest rate risk, we use duration. And the definition of duration is the sensitivity of a bond price if the yield to maturity or if the interest rate change, how the bond price are going to change. So this is a percentage change of yield to maturity, and this is percentage change of the bond price. And of course, the meaning of duration is straightforward, right? And this is a negative sign because they have negative relation, but we don't want duration to be negative, so we put additional negative sign here. And then this is just mathematical definition of duration, right? How to calculate duration? Duration can be calculated as weighted average of payment time. So you can say this duration equal to weighted average. So this W is a weight, and T is a payment time. T equal to 1, 2, 3, all the way to maturity, right? So T is the time of each payment, and W is weight. Then mathematically, the weight has an expression like this: cash flow of each payment over 1 plus yield to maturity of a power T and over the bond price. And so remember, if you got a duration like this, what's the unit of your duration? The unit of your duration would be the unit of small t, right? T equal to 1, 2, 3. But 1 means 1/2 year. Is that clear? T equal to 1 means 1/2 year, 2/2 year, 3/2 year, because typically coupon is paid every half year. So if your duration equal to 4, eventually if you got duration equal to 4, that's 4/2 year equals 2 year, right? So that's a little bit tricky. And how to prove this? I said this is just formula. How do we get this formula? Why this weight is written as this form? The proof is actually straightforward. It's a little bit messy, but it's not really difficult. It's not really complicated. Remember, the bond price equal to the discounted value of future cash flow, right? This is familiar well. This is a formula well familiar. We just make first order derivative. Remember the basic calculus, dP over d yield to maturity, right? Then over price. Then dP over this d yield to maturity, then you just make the first derivative of this term. Then the first derivative of this term will become, because you have a t here, right, minus t over, so you have additional 1 plus yield to maturity because your power will increase 1. So that's first derivative of the first term. And the first order derivative of the second term, basically the same, right? So this is a basic calculus. Then you just reorganize the whole thing a little bit, put this term 1 plus yield to maturity to outside of this bracket and put this price inside this bracket. This is just change the order of those terms. But then why do I want to write the whole thing this way? Because look at those things in the bracket. It is exactly the definition of duration. Remember, duration is defined by the weighted average of payment time. T and capital T are payment time. Then all those things before the time is weight. This is a weight, and this is another weight. So the weight can be written as cash flow over 1 plus yield to maturity, a power of T over price. Then if this whole thing is duration, then we just rewrite it as duration here. Then we got this dP over d yield to maturity over price equal to this 1 over 1 plus yield to maturity minus then times d, then we can rewrite the whole thing simply as dp over p equals minus duration times d yield to maturity over 1 plus yield to maturity, right? And remember, our definition of duration is something like this. So this is roughly, we prove it, if this delta p and delta yield to maturity is small enough, then we can go from this first derivative result all the way to this delta result, if delta is small enough. I will talk about if delta is not small enough, there will be small correction we need to pay attention to. So far so good. So that is how we prove that duration can be written as weighted payment time, right? Then we just put in some numbers to do calculation, just for example. So example is if we have a coupon bond 9% paid semi-annually and have par value 1,000, yield to maturity 10%, and maturity is 2 years. So what's the bond duration? Remember, duration is weighted payment time, and weights can be written in this form. Then there are 4 payments, right? Because maturity is 2 years, so you have 4 future payments, payment 1, 2, 3, 4. And the first payment is just coupon payment, coupon payment, coupon payment. The final payment is coupon plus your par value. And this is T, right? The small t is payment time. The first payment time is 1, 2, 3, 4. These two actually together, but I write it in 2 separate ways. But this is the same payment, the payment in 2 years. Then you need to calculate the weight. The weight is present value of payment, this numerator, and over the price. Price is denominator. Then this is a weight. I don't want to go very detailed, but this is just weight. Then you times each payment time with weight. And eventually you got each of those terms. Then duration is sum of all those terms. Then you got the duration. Of course, the number here is not very precise because I just use 3 decimals here. And how about if a zero coupon bond, if a bond doesn't pay any coupon payment? If there is no coupon payment, suppose the maturity is still 2 years, 4 half years, payment 1,000. Then the thing is, your weight is always 1 because you have only single payment. Then only single payments, then the weight of course is 1 because the sum of all your weights is 1, but then you have just 1 term. So this single term has a weight 1. And this single term has payment time 4 half year, then your duration is simply 4. So what does this tell us? This tells us if there is a zero coupon bond, then duration would equals the maturity. Then duration and maturity would be the same. So duration equal to maturity for zero coupon bond, and duration is shorter than maturity for coupon bond. Maybe still you in the later half of this lecture, I will talk about why we need duration, because after we get duration, we can do some useful application of duration. But the first half of our lecture, we just look at how we calculate duration. Then what determines duration? This risk, this interest rate risk. Duration of zero coupon bond equal to maturity. I have talked about that. All else being equal, duration is lower if the coupon rate is higher. So duration depends on coupon rate. This is a negative relation. Coupon higher, then duration lower. So the highest, all else equal, the highest possible duration is 0 coupon, right? 0 coupon bond has highest possible duration. 0 coupon bond has duration equals to maturity. All coupon bond has duration smaller than maturity. All else equal, duration is lower if the yield to maturity is higher. So still, this is negative relation. Yield to maturity higher, then duration lower. And all else equal, duration is generally higher if the maturity is longer or maturity is higher. So duration depends on coupon, depends on yield to maturity, and depends on the maturity, which can be seen from this graph in your book. So the duration depends on, first of all, duration depends on coupon rate, right? So 0 coupon rate, if the maturity is same, 0 coupon rate always has the highest possible duration. The vertical axis is duration, the horizontal axis is maturity. So 0 coupon bond has the highest possible duration. So if your coupon rate is higher, duration is lower. That is our first, this rule. The second rule said that all else being equal, duration is lower if yield to maturity is higher. For example, if you look at this gray curve and this blue curve, they have yield to maturity. This yield to maturity is 6%, but this yield to maturity is 15%. And lower yield to maturity give you higher duration. This is our second rule. The final sentence is all else being equal, duration is generally, remember the keywords is generally, not 100% necessarily, generally higher when the maturity is higher. So typically, this is an increasing curve. When your maturity gets higher, longer, then your duration gets higher. But there is exception. For example, the dot blue curve for the 3% coupon yield to maturity 15. Initially, it's an increasing function, but eventually it goes down a little bit. So in this case, it's not necessary so. But generally it's right to say duration is higher when maturity is higher. So this is not 100% correct. And in real world, some practitioners often do something called modified duration rather than duration. But the relation between duration and modified duration is very simple. You just divided the duration by 1 plus yield to maturity. Then you have modified duration. So why? Because remember, this is our definition of duration, right? If you have duration over 1 plus yield to maturity as modified duration, then this definition simply become this one, right? Then delta P over P equal to modified duration times the change of yield to maturity. So basically, just a little bit mathematical change, but based on the same equation. So I just use the same number to calculate the modified duration, exactly same as our last example. So I don't want to repeat everything the same as before after you got duration. Then what modified duration is, finally you want to divide this number with 1 plus yield to maturity. That's all. Okay. And probably it's sort of, if you really want to use some numbers to calculate, in my email box I have this. Did I post that? Sorry, give me a second. So in our slides, I just step by step show you how we calculate duration. But in practice, you don't have to do this. I'll just show you how this calculation match the mathematical definition. The mathematical definition. How this calculation steps match this mathematical definition. But in practice, there are a much easier way to calculate duration. For example, in Excel, given settlement date, given the maturity date, coupon rate, and yield to maturity, this is our example, right? Remember, this is just our example, 2-year maturity, coupon rate, and yield to maturity 10%. Then you just use this function. In Excel, you just have the settlement date as input, then the maturity as another input, and coupon rate another input, then yield to maturity. Then this 2 means this coupon paid twice per year. Then it gives you duration directly. So you just want to call this function, then you're done. Remember, in this Excel function, the unit is years. And if you times this cell by 2, you got half year. So basically the same. Then this is what we get, 3.746, right? 3.746. So this is the duration what we get. Or if you have financial calculator, you can basically do the same thing. So nowadays, it's become a function. Many software can easily give you duration as long as you have input variable, all those input variables, and it's easily to calculate duration. Then I use the same example. The question changed a little bit. Suppose the yield to maturity increases from 10%. Now this is 10%, right? From 10% to 11%, the interest rate changed. What's the duration implied price change? So remember, duration measure interest rate risk, right? Suppose we have interest rate change. So what does duration imply? The price change. And remember, duration equals the percentage change of price equal to modified duration times the change of yield to maturity. If yield to maturity go from 10 to 11, what's the delta yield to maturity? You should plug this in. 1%, that's wrong. Yield to maturity is semi-annually compounded semi-annually. Annual rate compounded semi-annually. So if I said the yield to maturity go from 10% to 11%, it's actually you need to put 0.5% here rather than 1% here, because this is all based on half year, right? So half year rate go from 5% to 5.5%. The delta yield to maturity is 0.5%. Right? And of course, the modified duration, we already got this number from our last page. So I just plug this number here. So this is what we get. Then the percentage change of price would be negative 1.784%. And what's the price change? The price change would be price times this percentage change of price. Very easy. Then this is the price change. So this is called duration implied price change, right? So we just use duration to calculate its implied price change. But what is the actual price change? This is implied price change. But of course, after you have a new yield to maturity, you can just use the basic bound price formula to calculate the new price. This is a new price if your yield to maturity is 11%. Then the actual price change would be the new price minus the old price. So this is the actual price change. 17.32. Record what we get here. The duration implied price change 17.52. Close, but not exactly the same. They are close, but not exactly the same. So the duration implied price change is not precisely equal to the actual price change of the bond. Little difference. Why? Yeah, that's right. That's right. Because we get this equation based on first derivative, right? Then, but first derivative, the assumption is this change should be small enough. But here, our change is small, but not that small. The change of yield to maturity. So there is tiny error. I think this is what you mean. We get this formula based on first order derivative. We say this, because of this, then we have that. But this is just approximately true if your delta yield to maturity is small, tiny. But if you have not really that small change, then there is some error terms, right? So we can graphically to see these error terms. Suppose originally our interest rate is here. This is the price. This is our interest rate, yield to maturity. Suppose originally our yield to maturity is here. Suppose the yield to maturity decrease of this amount, go from here to there. It dropped. Then the duration implied price change is from the first order derivative. So this is the green part. The first order derivative is the slope, right? So the green part is the duration implied price change. But the actual price change is green plus the red one. So this is the real price change. So there is the red part is a little error, right? So this graph just tells you this implied price change could be close, but there is tiny errors. The same thing can work if your interest rate increase. Then your implied price change will be bigger than the real price change. And so this is where those small errors come from. So therefore, in summary, duration only approximates the price impact of yield change or interest rate change. Fundamentally because this price-yield relationship is convex curve. It's not a linear, it's convex. So that is how the error come from. And of course, we can say it's good approximation only for small yield change. But suppose the yield change is not small, the yield to maturity change or interest rate change is big, then what else we can do if there is error? Then we can use another thing. Duration is still useful, but because of this error, we can also use something called convexity. So the definition of convexity is here. If this convexity is the rate at the slope of price-yield curve change. So this is the slope of the price-yield curve change. So actually, this convexity just like mathematically what it means. It means how much is this curvature of this curve. Is this very close to a linear function? Then the convexity would be very small. But if this curvature is very much apart from a linear curve, then this convexity will be big. So convexity is a measure of the rate at the slope of that curve change, right? So the convexity bigger, that means the first order derivative change a lot. And the starting point is the same thing. We go from the bond price. This is basic. Then, because this is a change of the first order derivative slope, so this is actually a second order derivative. a change of the slope. So second order derivative, but because I'm not focusing on those mathematical deduction, I just skip this deduction. Eventually, if you really wonder how I get it, you want to do a Tanner expansion, right? If you can do it by yourself, it's not required. Do a Taylor expansion of this part and looking for the next term. And the next term would be something called convexity. And this is mathematically, the convexity is expressed in this formula. And it's a little bit not very intuitively straightforward because you have t squared plus t. So it's not very intuitively straightforward, but mathematically it's true. Then, once we have convexity, then we can more precisely to make the correction of the small errors in the duration implied price change. The first term is duration implied price change if you have a delta yield to maturity, right? If you have change of yield to maturity, the first term is called duration implied price change. But now we have convexity, then we can use convexity to compensate this pricing errors. So this is how we compensate this pricing error. And I just skip this because this is basically, I follow this definition I just follow this mathematical definition to calculate the convexity of the same bond. If you do it step by step, you can eventually find a number like this. If you want to use financial calculator, you will get the same number, but let me just skip these numbers, right? Right? Then, suppose the same example, if the tiny change, not that tiny, there is a 1% change of yield to maturity from 10% to 11%. Originally, we said that duration implied price change, this is what we calculated before. And we know that this implied price change is not really that perfect. Then we can have duration plus convexity implied price change. So you have additional term here. Once you have additional term here, second term is small, but it's critical. Then you have a new price, implied price change. This is duration plus convexity implied price change. And this implied price change would be exactly very close to the new bound price, almost the same, right? So this is how we mathematically correct that small error. But are they perfectly the same? Probably not, because they are fairly close enough. But remember, if you have a Tanner expansion, the second term, third term, all those higher order term, we just don't need to pay attention to them, because convexity will give us a good enough result. Well, a tricky thing is if you are doing this calculation, pay attention to this unit. There is nothing, it's just a little tricky thing. The unit of duration is half year, right? The unit of convexity is half year squared. So it's a little bit strange because of the mathematical definition, right? There is a square here. So, but you don't have to pay attention because this half year square is just cancel out. Why you have a half year square here? Because according to that, yield to maturity is has a unit like this, right? You have number, but every half year. So this is so this half year square just cancel out, just like this half year cancel out. Eventually, your percentage of price change is just a number. This is just a number. It has no unit. It's just a number. So if you want to write everything in terms of year, then everything becomes a quarter of those size. But eventually, the final result would be the same. So some people or some textbooks, they prefer use year as unit. But some other textbooks, they just use half a year as unit. In our course, we use half a year as our unit, okay? We use the first convention, right? But if you say something different, maybe very likely it just come from that unit choice. I just give you a homework for practice, and it's very similar. Actually, it's from our last year's final exam, but probably I will not use the same question this year. But you have idea the level of difficulty of our final exam? I don't think it's really difficult, right? You already have an example like this, then this example is very similar. I think if once you do this homework, you'll get a little bit confident for this final exam. Okay. And investors view convexity as an attractive characteristic of bond. Convexity is attractive. It's measure of asymmetry. Why it is? That means if a bond, all else equal, if a bond has higher convexity, the bond would sell at a higher price. Why? Convexity is good. It's just from this simple graph. If the interest rate go down, if you have higher convexity, which means the red part would be bigger. So if the interest rate go down, your price change will be even higher. So this green part is bigger. But unfortunately, if the interest rate go up, then your price drop. But because of this red part is bigger, then the price drop is not that big. I mean, relatively, the price drop is smaller when your red part is bigger. So convexity is higher means your red part is bigger or longer, and that is good. When the price go down, you go down less. When the price go up, you go up more. So that's why. That's why convexity is an attractive characteristic of bond. And it's a feature that investors have to pay for because everybody knows it's good. So you have to pay more for convexity, or else same bonds with greater convexity will be more expensive, right? So let's have a 10 minutes break, then we will continue.
Yeah, you use second years. So I think the default is that you just have various functions, and then the default is that really?
All right. Just a thing about your assignment. Students come with a very good question. When you do this, this is very critical, right? I'm not going to grade your result based on this number, but this is an important block to get your final result. When you do variance-covariance matrix calculation, you can use the covariance function. But remember, there are two types of covariance function: sample covariance, which is covariance.s, and population covariance, covariance.p. So which is the right one? The right one is sample covariance. So covariance.s, then you look at the covariance between the first and second, and so on and so forth. So don't forget this, because there will be tiny difference if you use population covariance or just covariance. So this is something that really matters. Yeah. Okay, where we are, okay, now we move on. Talk about immunization. So what is immunization? Immunization is a strategy, investment strategy used by investors to shield their overall financial status from interest rate risk. So they just want to remove interest rate risk, and this immunization is a strategy to eliminate interest rate risk, not completely, but effectively. So why people want to do that? Because some investors will make payments after a given number of years, so they need to protect the future value of their portfolio. So if you're a household investor, suppose your children are going to go to college in 5 or 10 years, then you have to pay the tuition in 5 or 10 years. So that means the future payment is the application, and your investment horizon would be 5 years, say. Then, but you are not sure about the future movement, future change of the interest rate, but you want to protect your future value of your portfolio. Another motive is that some financial institutions need to protect the current net worth of their portfolio against the interest rate fluctuations. So they're similar, but one is for net worth, one is protect future value. And we just use example to see this. right? So the case one is, suppose the investor wants to protect the future value of its portfolio, of course its bond portfolio. If the investor has a fixed obligation to pay in 5 years, which means after 5 years, this investor has to pay certain amount of money, so it's an obligation, either for consumption or for debt, whatever. We just call it obligation in 5 years. So today, the investor's portfolio holds 10 bonds. The bonds has 8% annual coupon rate. So this is the annual rate. This is a special case. This is not semi-annual. It's just 8% paid annually in this particular example, and 6 years to maturity. And market interest rate, 6 years per year. This is also true interest rate. And coupon income are reinvested to the market interest rate. And then what's the duration of his portfolio? Remember, the year to maturity, all the 10 bonds are identical. They have 6 years to maturity, right? But the duration of his portfolio is shorter than maturity. Why? Because this is a coupon bond. For coupon bond, duration should be shorter than maturity. And if you do calculation, like use that duration function, it's easily to get this duration of this bond in 5 years. You can calculate to confirm it. Okay, we just skip this calculation. So the duration of this investor's portfolio is 5 years. So now if investor's portfolio duration is equals to investment horizon, remember, his investment horizon is 5 years, right? Because he needs that money in 5 years. So investment horizon initially is 5 years. Now he artificially make the duration of his portfolio 5 years. Then they are identical. Then what's the value of his portfolio in 5 years? We just look at these numbers. And this is an example again from the textbook. I just think this is a good example, so I copy it. So there are 3 different scenarios. The first scenario is if there is no interest rate change, if the interest rate remain at 8%, so interest rate doesn't change, then every year you got coupon payment, right? Because remember, this setting is a year coupon bond. And after you get each coupon, then you reinvest your coupon with the same interest rate, 8%, over the rest of time. So the first coupon, you reinvest at 8%. Eventually, at the end of 5 years, you got the money of this from first coupon and reinvest the second coupon at end of the 5 years. This is the second coupon will generate a cash flow like this. And third coupon, so on and so forth. And this is the final par value payment. And this altogether, this amount of money is the final cash flow you can eventually have at the end of 5 years, right? This is just a number. So in 5 years, at the end of the 5th years, this is the amount of money you can eventually get if the interest rate remain. Okay, so of course, this is too ideal because in the future, maybe the interest rate change. So suppose tomorrow, not next year, just tomorrow, the interest rate just fall to 7%. So today, 8%, tomorrow become 7% instead. Then your reinvestment rate would be 7%, even if your coupon is unchanged, but the reinvestment rate is smaller. But at the end of the 5th year, you sell your bond. Because your bond hasn't matured yet, the maturity of bond is 6 years. So when you sell the bond still have 1 year to maturity to go, right? So you sell your bond, then you got, this is the price of that bond at the end of 5th year. And you put all those cash flow, sum all those cash flow up. This is the total cash flow you can get at the end of the 5th year. And a good thing is, those two numbers are fairly close to each other. If the interest rate doesn't change, you got this amount of money. If the interest rate drop from 8 to 7, still you got this amount of money. The difference is too tiny. Let's just skip this difference. Let's say you got the same amount of money. The second scenario is if the interest rate increase tomorrow the interest rate increase to 9%, and the same thing, you reinvest your coupon at 9%. At the end of the 5th year, you sell this bond at a bond price of 9,900 something. Then the total cash flow you can get at the end of the 5th year, a number like this. Again, this is fairly close to what the two numbers before. So what does this numerical example tells us is, if your portfolio duration is equal to your investment horizon, in this example, your investment horizon is 5 years, right? Even if your maturity of your bond is 6 years, but your investment horizon is 5 years, but the duration of your portfolio is also 5 years, then if those two match, then the value of your portfolio in 5 years at the end of the 5th year would be unchanged. It doesn't matter the interest rate go up or down. At the end of the 5th year, you got the same amount of money, right? So the interest rate just eliminated. You don't need to care about the interest rate fluctuation anymore. So that's the whole thing. That's the whole point, to protect the future value. If you really need some money in 5 years, make the duration of your portfolio equals your investment horizon. Then the interest rate fluctuation will not affect you. That's very good, right? So why is it possible? You can mathematically this is very easy. So this is So this is a time. Suppose T star is today, okay, right? And maturity is capital T. Of course, when you have suppose you have a coupon bond, the coupon bond the price will go up. Suppose the the coupon payment is much smaller than yield to maturity. So today's bond price is lower than the par value. But when the time approaching the maturity, then the bond price will approach the par value, right? This is what we learned last lecture. So this blue curve just show you that if the time approach maturity, then the bond price will approach the par value, something like par value. But suppose there is an interest rate change. Suppose today the interest rate suddenly drop. Suppose not the interest rate. It's not drop. Sorry about that. The interest rate rise a little bit. Interest rates rise, then your today's price drop, right? The price is negatively dependent on interest rate. So if today interest rates rise a little bit, then your price drop. So that's price change. But remember, if your interest rate rise, then if you reinvest all your coupon into all the way to the future, then eventually at maturity, you got a par value, and you got all this reinvested coupon, then eventually your value will be higher. Why? Because interest rate got higher, then you got more money from your reinvestment of your coupon, right? And if you hold the bond all the way to maturity, at maturity you got par value, same, but your reinvestment of coupon give you a higher cash flow. So that is why eventually, if you hold all the way to maturity, the cash flow would be a little bit higher if this interest rate become higher. But the interesting is today, the today, interest rates rise will cause the price drop, but eventually at maturity, interest rate rise will cause the value increase. But somewhere in the middle, those two things will cross. And this is the duration. Somewhere in the middle, if your investment horizon is right at this duration, then the value is constant. No matter your interest rate go down or go up, then your portfolio value would be constant, unchanged. So this is a nice thing about duration. So this curve just mathematically shows you if you match duration with your horizon, then interest rate fluctuations are not going to affect your future cash flow anymore. So just like was said here, the future value at the horizon date would be unaffected if those two are equal. So in other words, the future value of your portfolio is protected. So that's one way to use this duration. Another way to use duration is that we want to protect current net worth of your portfolio. But remember, the current value always changes. If the interest rate changes, the current value always go up and down. That's not something we can avoid. But here's we're talking about some financial institutions like banks or funds. One important feature of those institutions, they have both asset and liability. For example, the commercial banks, they have liability to all those depositors, all those customers. And they have asset if they have commercial loans to all those. So for financial institutions, they have asset side and liability side. So both sides suffer from this interest rate fluctuation risk, right? If interest rate change, the value of liability also change. The value of asset also change. So interest rate change will cause price risk both on the asset side and on the liability side. So what's immunization for this case? They want to build an immunized portfolio, then the net price change cancels out, which means the value of asset will track the value of liability. So if the interest rates change, they want both sides change the same way, so they cancel out. There is no net risk. So the key thing is net risk would be eliminated. They cannot eliminate the risk for either side, but they can eliminate the net risk. So it's straightforward how they can do it. Suppose we have a bank and bank liabilities, consumer deposits, and bank aside like commercial loans. We just want to match the asset and liability durations. So the duration of asset, let me use capital A to symbol it. So the amount of your asset times the duration of your asset equal to the value-weighted duration of your liability. So value-weighted duration of your asset equal to value-weighted duration of your liability, then this is how this bank should do this immunization. Right? Let me use an example to show this. So suppose this institution called XYZ Corporation, it has liability. This is liability side. It has 1 million liability to pay in 10 years. And current interest rate is given and it's compounded semi-annually. And what about the asset side? Then the asset side will have two bonds, 30-year coupon bonds and 10-year coupon bonds. They have coupon rates, different coupon rate. Let's call them bond 1 and bond 2. And this XYZ firms want to have this portfolio immunized against interest rate change. Right? So to do it very simply, the liability duration equals to the asset duration. So what's the duration of the asset duration? First, we need a step-by-step calculation. So the interest rate is given 4.5 per half year. So the present value of liability is very easy to do it. And the bond price, given all this information, the bond price can be calculated. Bond 1, bond 2, and duration can be calculated. I just skip that because given all this information, it's easy to get all those numbers. So the duration of bond 1 and bond 2 are easy to get. Then eventually, we need to have this to satisfy. First of all, the present value of your liability equals the present value of your bond. So your asset side and your liability side are equal. The second thing is your duration of your asset side. This is duration of your asset side, right? Bond 1, bond 2. And this is the duration of your liability side. Okay? So you want to match the duration of your asset side with the duration of your liability side. Then we can simply solve this equation, right? We have two unknown variables. The present value of liability is known. We already have the present value of liability. So this present value is known. So we have two variables, two equations. So this is like middle school mathematics. Eventually we can solve these equations to figure out and the V1 equal to the value of first bond equal to some number, the value of the second bond equal to another number. And remember, the bond price is, we already know the bond price, right? So the question is, how many bonds should we purchase? So the bond value of the first type of bond times the bond price, then we need to purchase 424 type 1 bond. And again, for the bond 2, type 2 bond, we have this value, and this is the price of each bond. Then we need to hold 108 type 2 bond. So the answer is, okay, this XYZ, sorry, this is typo, this is XYZ firms should purchase 424 type 1 bond and 108 type 2 bond. Then achieved. We can double check whether this is really. So let's just double check with whether the value of the portfolio is truly immunized against interest rate change or not. Suppose initially this is our initial interest rate, 9%, right? This central column. Initially we are at 9%. We know the present value of our asset side. This is present value of asset side. Okay, we have bond 1, bond 2, and this is our present value of our liability. Suppose the interest rate go up from 9 to 10, go up, then because when the interest rate go up, the bond price go down, right? Which means the asset side, the value of the asset side will go down. But the good thing is about the value of your liability side also go down. So asset side go down, liability side go down, but basically they are still same. So this risk basically cancel out, right? So you have smaller asset, but you have smaller liability. Eventually, you don't have to worry much about that. The same thing, if the interest rate go down, then your bond price go up, then your asset side will have a higher value. That's good for the asset side. But the bad thing is, if the interest rate go down, your liability also go bigger, then still they roughly the same. So this is how immunization will make this institution don't worry much about the interest rate fluctuation. But still, they are not 100% precise, right? Even if here your liability and present value of your liability and present value of your asset are fairly close, but if the interest rate change, because the difference is right here, right? But if the interest rate change, the difference will go to here, maybe 1% different, 1% different, or less than 1% difference. So it's a good match, but not 100% precise. The question is why? I think there are two main reasons. The first reason is we don't really, this is duration, right? This is a match of duration. We don't talk anything about match of convexity. So we just ignore convexity in this question. So the convexity will cause this tiny difference, small difference. If the interest rate change, not very small change. So the first obvious answer is because of convexity, you cannot be 100% precise. Another reason is the integrals of bounds, right? Why? Because here, mathematically, we need this value of the type 1 bound. But remember, you can only buy an integral number of bound, right? So eventually, this is mathematically you have to have an integral here. So that is where originally it can have a small error, right? So the convexity and also the integral of bounds means that immunization can be 100% perfect, but it's good enough. Another thing about the immunization, because immunization, let me ask a question here. So this immunization is so good, you have to match your horizon with duration. But suppose you invest to stock portfolio. Remember, we are just talking about bond portfolio, right? Suppose this is not bond portfolio, this is stock portfolio. You still have investment horizon, but then there is nothing you can match, right? There is nothing you can match. Even if your portfolio you will need money in 5 years, but you cannot say that the duration of stock portfolio, there is no such thing as duration of stock portfolio. Because the main source of risk for stock portfolio is the standard deviation variance. It had nothing to do with interest rate fluctuation, right? So that's a significant difference between bond portfolio and stock portfolio. That's why bond portfolio can sometimes be attractive. It's attractive because you can do something called immunization to kill the risk and to get a fixed amount of money if you really need that amount of money in 5 years. Okay. But negative side of immunization is not, I should not say negative side, but a more tricky side of immunization is once you make this immunization today, but in the future you cannot just let it go. You still need to spend time to rebalance the immunized portfolio. Because in the future, if the interest rate change, an investor must rebalance the portfolio to align the duration, of the portfolio with the duration of your investment horizon. Which means in the future, if the interest rate change, this match of duration would not work. You have to change the portfolio to make those two equals again. And the second thing is, even if interest rate doesn't change, a mismatch of duration could happen solely because of passage of time. So what I mean is here, suppose today you want to do an immunization, then you have, suppose you have 0 coupon bond, and this is your asset side, and you have 15% coupon bond, year to maturity 6%, and the vertical axis is the duration, right? Suppose you want the asset side equal to the duration of liability side, then you just purchase a 10-year maturity 0 coupon bond and a 16-year maturity 15% coupon bond. So you have you just purchase a 16 10-year maturity coupon bond and 10-year maturity zero coupon bond, then you got immunization, right? Because the duration equal, but initially their duration is equal. But the question is, after 3 years, if the time just passed by, then this 10-year zero coupon bond became 7-year zero coupon bond, right? After 3 years, then the 10-year zero coupon bond will become 7-year zero coupon bond. So it moved from this black dot to the red dot. And this 16-year coupon bond will become 13-year coupon bond. I'm talking about maturity, right? So it moves from this black dot to that red dot. Then this duration, their duration would be not the same, right? Initially the same, but just because the time passed, the duration will become mismatched. That means if you really want to do the immunization, you need to recalculate and change your portfolio composition, right? So that is what rebalance means. Even if interest rate doesn't change, a mismatch of duration can happen solely because of the passage of time, right? And so the portfolio must be rebalanced in response to the interest rate or duration change. So in order to, for those portfolio remain immunized. But there is trade-off because rebalancing involves transaction cost, right? So if you are a bond portfolio manager, you want to take a trade-off between a perfect immunization and the cost of rebalancing. So if you want to achieve perfect immunization, probably you want to do the rebalancing every week or every month, but that's costly. So sometimes we just don't want to achieve perfect immunization. Then I just briefly talk a little bit about this mortgage-backed security. Remember, I talked about this before, right? I said this is one of the main reasons caused that financial crisis, this mortgage-backed security. And one reason is those rating agencies, those rating firms, Standard & Poor's, Moody's, and Fitch, they are like a monopoly of information, but they just give a wrong credit rating. Then this market collapses a lot, right? But still, I said that market collapsed a lot, but still, this market is still significant. I'm not saying that this mortgage-backed securities just totally disappear. It's like a break of bubble, but they are still there. Even today, this is 2015. In terms of size, this mortgage-related security are still significant. Remember, this is a total market of the fixed income market, right? The largest part is the U.S. Treasury bonds and Treasury notes, something like that, government bonds. And the second largest is still mortgage-related, mortgage-backed securities. And they are a little bit bigger than the corporate bonds. So still a very important type of security in terms of size, right? It's just some issuers of those mortgage-backed securities pool all those mortgage loans and securitize the loan pools and sell those securities to investors. And I talk a little bit more about this. One feature of this mortgage-backed securities, those securities are very similar to a portfolio of callable bonds. Remember, callable loans or callable bonds. So what callable means? It's just the option of the borrower. They have option to pay back earlier than the maturity date, right? So if you borrow money to buy a house, suppose the mortgage is 30-year mortgage, right? Suppose you buy a house, you borrow money from a bank, the mortgage is 30-year mortgage, but you have the option to pay all your loans back before that 30 years, right? You don't want to really do it as long as 30 years. You can, if you have money in the future, you can pay it back in 15 years or even in 10 years. It depends on your financial situation, but it's always an option for you. So the borrower can pay back earlier than the maturity date. So it's very similar to callable bond. So the homeowner has right to repay their loans at any time. And then the relation between the bond price, callable bond price, or the relation of the mortgage-backed security and the interest rate would be a curve like this. Because for a regular bond, you just have a negative curve like this, right? For regular bond, let's go back a little bit. For regular bonds, you just have a curvature like this, right? Value versus interest rate. This is very nice. This is just for regular bonds or straight bonds. But for callable bonds, the relation is a little bit complicated because once the interest rate is smaller, which means current value become higher, then probably the homeowner wants to refinance their mortgage, just borrow more money to pay the old mortgage back. So that is why when the interest rate go down, the possibility of early payment will become higher and higher. So it's very much like a callable bond. But why this yield curve, why this price yield curve matters? Because we are talking about duration and convexity, right? Convexity for this type of security is a little complicated. The convexity of this part is positive convexity because it's convex curve. This is a convex part, convex curve here, but this part is concave. This part is a concave, which means negative convexity. So in this range, this security has negative convexity, and in this range, it's just like an ordinary bond. It has positive convexity. It's all from the second derivative of the curve, right? Mathematically, second derivative of this part of curve is negative, and the second derivative of this part is positive. Okay. How about the duration of this mortgage-backed security or the duration of callable bonds? The mathematical formula is also a little bit different. The convention is to compute something called effective duration rather than duration. This is a new phrase. It's called effective duration just for callable bonds or for the mortgage-backed security. So what is effective duration? It's very similar to the duration of regular bonds. The percentage change of price over this delta R is a shift of market interest rate. Remember, originally, in contrast, for just a regular bond, the duration, the modified duration is percentage change of price over the change of yield to maturity. This is what we just learned. But for here, this is not the change of yield to maturity. This is a shift of market interest rate. Eventually, it's actually a parallel shift of yield curve. We're going to talk about yield curve next week, so at this point of time, you don't have to pay attention to this yield curve. But anyway, mathematically, calculation of this is not that easy. It depends on some kind of pricing methodology, because eventually for a callable bond, there is a call option. So eventually you have to price an option price. You need a complicated model to calculate dP over P over delta R. So our course, we don't cover how to mathematically calculate this effective duration. I just need you to know the definition, that's all, right? The definition of effective duration. And in practice, if you work in financial industry, you will build complicated model the model will give you a relation between callable bond price or mortgage-backed security price and the market interest rate. And if you have that complicated model, then the computer can give you effective duration if you're really working in the industry. But here we don't have to go that deep. Another thing about this mortgage pooling is that it can give risk to a set of mortgage-backed derivatives. A good example is so-called CMO, collateralized mortgage obligation. So what is CMO? It's just, first of all, you have a pool of mortgage rights. That is at the beginning of your story. You have a pooling of mortgage. Then after you have a mortgage pooling, you can do a little bit of financial engineering based on that pool. So the underlying mortgage pool can be divided into different tranches. You can do a very simple financial engineering. You have a pool of those mortgage. You can divide those mortgage into different tranches. I will explain what tranche means. Just each with different effective duration. So this is an example. This is a whole mortgage, right? Suppose the mortgage is 15-year mortgage. That's a typical if you buy a house, 15 or 20 years mortgage. And each year you will pay back. If you're a homeowner, at the beginning you will pay a lot of things. And this deeper dark means the principal you pay. And the lighter dark is the interest rate you pay. So you can see that at the beginning, a lot of your payments just cover the interest rate, right? And later on, if you pay more and more, then most of your payments go to the principal payment. But this is how your cash flow, right? You will pay back this amount of money across a year, pay it back. So this is the amount of cash flow. Suppose there is no early payment. Suppose there is no default. So this is the future cash flow of this mortgage, right? But once you have a pool of mortgage like this, then you can divide this future cash flow into 3 different tranches. So this whole mortgage can be divided into A, B, C. So the sum of A, B, C equal to the whole mortgage. But the first tranche is just cash flow in the recent from 1 to 5 years. So this is a recent year cash flow. This is called short pay tranche. And this is called intermediate pay tranche because the focus cash flow is somewhere from 5 years from now to 10 years from now. And this is called long pay tranche. Basically, the cash flow is those cash flow long from far away from today. So what's the purpose? What's the purpose of dividing this total thing into A, B, C? The whole purpose is A, B, C has different duration. Can you see that? This has a shorter duration. This has a longer duration. And this has intermediate duration. So this is what I say. Because this has a recent cash flow, of course the duration is shorter. This is a very long pay, so the duration is much longer. The whole thing is each tranche will have different effective duration. Each tranche has different effective duration. Then each tranche has different interest rate exposure, right? The duration is higher means the interest rate exposure is higher. The duration is lower means the interest rate exposure is lower. So by this way, different tranches can be designed to target different investors because some investors don't care much about risk. Then they can buy the higher risk tranche. But some investors really care about interest rate risk. Then they are going to buy this low duration tranche. And also, if investor has different investment horizon, they can work because if you need the money in 3 years, but he needed money in 15 years. We have different investment horizon, right? But then you're probably, if you need money in 5 years, you are going to buy a tranche like this. You will make a portfolio of securities like tranche A. But if I am really a long-term horizon investors, I'm going to buy a security like long pay tranche. So by this very simple way of doing financial engineering, the starting point is the same mortgage. But because of this financial engineering, different investors, those investors with different investment horizon can buy the ideal securities they really want. So this is just do a little bit manipulation, not manipulation, do a little bit financial engineering to satisfy different investors. Because the investor wants to make their duration equals to their investment horizon, then they can eliminate the interest rate risk, right, to achieve immunization. So this is a simple way to achieve that. Okay, good. We'll just finish this chapter. I'll see you.